All right, guys, let's pick up where 4.3 and 4.4 left off. And this says Seth and Jay wrote the following explanations of why two triangles are congruent. We have triangle ABC. We have triangle DEF. Let's do a couple things before we get into it. Line segment AB is definitely congruent to line segment ED because they're both 5 inches. I don't know anything about BC, and I can see that its corresponding part would be FE. So I'm not going to put anything there, but at least now I know if I orientate this the right way, those would be the corresponding parts. AC and FD are congruent, so I'm going to go ahead and put my congruency marks there. And we know all right angles are congruent to all other right angles. Remember when we first talked about this back in chapter 1 and 2, I said these are some of those common sense things, but it's good to talk about them so that you see them right away when you're doing these types of problems. So let's look at what Seth wrote, and then let's look at what Jay wrote, and let's see who is correct, or let's see whose work we can adjust to try and prove that these are congruent or not congruent. So Seth says there are two pairs of congruent sides, AB and DE. We've said AB and DE are congruent. So I'm going to put a check there because I agree with Seth there. And AC is congruent to DF. Well, AC and DF are both 4 inches, and we've already set that with our congruency mark, so I agree there. And a pair of congruent right angles, angle C and angle F. So right now, Seth's is looking pretty good. And it says, so triangle ABC is congruent to triangle DEF by side-side angle. Now that's a bad word backwards, and we cannot use this. I'm going to say no to Seth only because he did everything right. He just failed right here at SSA. SSA is not a congruence criterion. And that just means we can't use SSA to prove congruence. Now let's look at Jay and see what Jay's done. Maybe we can just go back to Seth and figure out a better way to say that. Or we can just see what Jay did and we're good to go. Now he's saying the lengths of line segment BC and EF are 3 inches. So he's saying right here, those should be 3 inches or the same. I'm not going to put the 3 in there yet because I haven't been convinced that 3 is the proper length for that. But he is at least saying BC and EF are congruent, so I'm going to use the same variable there to move forward. Now they're saying since these are 3, 4, 5 right triangles, there are 3 pairs of congruent sides, AB and DE. Well, we already agree that AB and DE are correct in being congruent. AC and DF, we've also can agree that those are congruent. And what he's saying now is BC and EF is congruent. Now, he's ultimately going to use side, 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 but I would need a way to prove that BC and EF are congruent. And what we're going to be learning in 4.5 is actually something called the hypotenuse leg theorem. So we could do Fimble's class. And at the end of this, we'll just say by HL. But let's verify Jay's thoughts here. Well, if I have a right triangle, I can use the Pythagorean theorem, a squared plus b squared equals c squared. And we know that the right angle, the perpendicular marker, points at C. So this is going to be 5 squared. E is equal to, and now we know the legs when we use the Pythagorean theorem. We can do A or B. Addition's commutative. So we're going to do, we get to pick. I'm going to make X A. So I'm going to have X squared plus 4 squared is equal to 5 squared. And we can see that we are going to end up with, I'm going to move it over here, X squared is equal to 9. And then I'm going to change the color really quick just because we're getting a little jumbled. This means that if I take the square root of both sides, I can get, well, let's move this out a little bit. X is equal to plus or minus 3. But since we're dealing with lengths, this minus part makes no sense. So we're just going to say X equals 3. So by the Pythagorean theorem, we can say X is equal to 3. And this is in fact a 3, 4, 5 triangle. And what I will call these in class are Pythagorean triples. On your bonus assignment for this, you're going to discover a couple of Pythagorean triples and then verify them. So it just means the two smaller numbers squared, added together, and then taking the square root will always give you the third or the largest number. So again, 9 plus 16 equals 25. So technically, J is right, but that's a lot of work to prove J is right. What we're going to be able to do at the end of this chapter, and I'm going to give you a little sneak peek here, is do this. The hypotenuse leg theorem is what we're going to use. The first thing we want to do is ask ourselves, are these right triangles that we're looking at? Well, yes. So if our answer is yes, we can go to step 2. And these 3 steps will always get you a yes or no ultimate result so that you can then move on to either one of the other 4 criterion or just make a judgment that says, no, these are in fact not congruent triangles. So since these are both right triangles, my second question I need to ask myself is, are the hypotenuse congruent? Well, this point's here, and this is why I ask these questions in this order. I identify the right angle. That lets me identify the hypotenuse much more quickly. 5 is equal to 5, or since we're talking side lengths here, 5 is congruent to 5. And since our answer to question number 2 is yes, my third and final question, if I get a yes for this, I'm good to go. Do we have a corresponding pair of legs? Now, corresponding pair of legs doesn't mean on both triangles both legs are equal or congruent. Corresponding congruent pair of legs. What that means is if I look at one of the legs, do I have a congruent leg? That's also when I rotate these or do my rigid motions that would map onto each other. Well, if this swung up to here, then this 4 would definitely map onto this 4. So I do have a corresponding congruent pair of legs. And since I have 3 yeses, this is going to be doable by the hypotenuse leg theorem. If I get a no at any time here on any of these questions, I move on to one of the other 4 criteria: side, 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 angle, and angle, angle, side. If I can get a yes from any of those, then I have 2 congruent triangles. If I don't get a yes on any of those, then we're going to say cannot be determined. So make sure you have those 3 steps written down, and we don't have open notes on this one, so kind of memorize these steps. Ask ourselves, are these right triangles? Yes, move on to step 2. No, move on to the other 4 criteria. Second question, are the hypotenuses congruent? Well, the hypotenuse on both triangles is always opposite the right angle. Here we have 5 inches both times, so these are definitely congruent. And since we have a yes there, we can move on to, is there a pair of corresponding congruent legs? And the answer here is yes. Of course, with J's help, we know these are 3 and 3. So this could be your other pair of corresponding congruent legs. But let's actually look at what this theorem is in writing. Now, since we're watching this as a video, go ahead and pause it and copy it down. And then when you hit start, I'll be talking about it already. So one of the great things about the hypotenuse leg is, remember when I said we can't use SSA forwards or backwards? With a slight exception, your hypotenuse leg, if you end up seeing SSA or the bad word, there's a pretty good chance that if it's a right triangle, you're going to be able to apply hypotenuse leg instead. That gets us out of the hot water of using bad words in class. And it's just a little bit of an easier way to keep all of this tracked in our mind. So let's look at what I mean by if we end up with SSA or the other word, what we can do to kind of look at it a second time and see if maybe we can make it fit to the hypotenuse leg. I'm going to go from here to here. And now I know I'm going to do that because I already see there's no angle congruency here and there's no side congruency here. So that's going to give me my 2 strike rule, and that means I can't go that way anyways. And since we're all experts on that, I'm just going to go the right way the first time. Here, if I started at 1, I went around the non-right side, and I made sure that I hit the 2 marker and then the right angle. So I'm going to go this way. Missed the angle, hit the 2 marker, and now I'm back at the right angle. So I start with an S for the side congruency. Travel around, didn't have the angle, but I did get the double marker. So that's my second side, and then I ended up at an angle. Remember, all right angles are congruent. So I do have what would be SSA, but we can't use that. But what I want to tell you is if you're doing the test, or if you're doing the homework, or if you're just looking at this in life in general, and you see SSA or the other word pop up, stop what you're doing before you move on to something else, like angle, side, angle, or side, 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 and ask yourself, is there a right angle here? And if the answer to that is yes, then you've already answered one of your questions of the 3 for hypotenuse leg, right? Are these right triangles? Well, question 1's answer is yes. So my second question is, are the hypotenuse congruent? Opposite the right angle? Opposite the right angle? These are definitely congruent by the congruency marker, so yes. My third question is, do we have that corresponding congruent set of legs? Well, let's do the color change real quick. If I were to reflect this over this line, then it would be flipped where L is on top, N's on the bottom, which would orientate my right angle up to here. Then I would need to reflect it across this line, which would then put it in the proper positioning, and then I could just translate it over. And I can see that these two would in fact be corresponding and congruent. So this SSA, which we told you last class, get away from as fast as possible, in a right triangle has a very high chance of it being a hypotenuse leg theorem criterion, and we can now say yes, but never by SSA or ASS, but we will say yes by the hypotenuse leg theorem, which we have right here, theorem 4.8. So SSA is not completely useless. We still do not use it ever. But it does give us a hint that if we have a right triangle, there's a good chance we're looking at the hypotenuse leg theorem. So here we go. In order to apply the hypotenuse leg theorem, it is necessary for MN to be 5 and PR to be 9. Looks like we kind of have the answer here already for what we're asking. What information is needed in order to apply the hypotenuse leg theorem? Well, here we know we have 2 right triangles. So our first question is it a right triangle? Yes. So we have our start for our hypotenuse leg. Now, I know what the hypotenuse is here because opposite of my right angle is the number 9. And it says what information is needed to apply the hypotenuse leg theorem. That means I would have to know that my hypotenuse on this one was also 9. And then this is the part where it gets a little tricky. So let's just do this. So we have our congruent hypotenuse. Yes. Number 3 becomes the tricky part because I can't just arbitrarily pick one here. Because remember, the third question says corresponding congruent. And that corresponding means we have to pick the correct side. So in topic 3, we learned how to rotate, reflect, translate, glide, reflect to map these polygons or these triangles onto each other. I'm not asking you for the the line of reflection or this point of rotation or what the rotation needs to be. All I'm asking you to do now is use your imagination and ask yourself, how can I get triangle LMN to map exactly on top of PQR? And if I were to do that, this would have to rotate down so that this right angle's in the corner down here, right? And if I do that, this is going to put my L at top, my M here, and my N here. And then I need to reflect it. And actually, just let's do this so we're removing it. I'm going to put my point of reflection here. And that's going to do this for me. Now I know these are not to scale, but since we know these are rigid motions, the triangles, the images that I'm creating will be congruent to LMN, and we're trying to prove that it will then map on to this figure here. And now that I have my right angle corresponding to my right angle and my hypotenuse corresponding to my hypotenuse, I know that I now need this piece to be 5. And when I flip this, this is L, this is M, and this is N. So I can see that the other piece of information I need to know, so I need my corresponding congruent legs, and those would be MN being congruent to QR. So make sure you see what I did here is I drew out what I would be doing in my head. In my head, I would just rotate this. I would actually just leave it here in my mind and then flip it and then slide it over to make sure that these 5s are corresponding and congruent. Had I done all of this and my 5 was up here, then I would need LM to be 5. All right. Now, before we move on, I want to make sure that we have an extra chance to look at the Pythagorean theorem. So what I want to ask us is, if we know this must be 9 now, what must this side be? Well, my C is this, right? So this is automatically equal to C. I'm going to keep my variable out front and make that A, and I'm going to keep my known side length as B. And I can start my substitutions here. A squared plus B squared equals C squared. And I know C is 9, so I'm going to have 9 squared. And this is going to be equal to, substitute in for A, I get X squared plus 5 squared. And this is going to give me 81 is equal to 25. And X squared plus 25. Subtract 25 from both sides. And this is going to give me, what would be 60 there, so 56. And I know 56 is not a perfect square. So when I come here, I'm going to do a little erasing really quick. And I have some good news for you. In geometry, unless I specifically ask you to simplify it, we're going to leave that side length as the square root of 56. If you need help on simplifying these or doing the prime factoring of these, I have another video of this on my channel. Feel free to watch that one. Come to tutoring. Mr. Ding, Miss Walker, and I will all be more than happy to show you this. All right. So, with our right triangle, like I said before, if we see SSA or the bad word, we're most likely going to be able to use our hypotenuse leg theorem, right? Is it a right triangle? Yes. Or the hypotenuse is congruent? Yes. And do we have a corresponding pair of legs that are congruent? Absolutely. We can use the hypotenuse leg theorem. But let's say we had something where we didn't know the hypotenuse were congruent, but instead we were given these side lengths were congruent. Then I can do, well, let's mark it correctly. This would now just be side, side, side. If I knew that these angles were congruent, what is this here? Between 1 and 2. If I had these two, this would be side angle side congruence. So just because you have a right triangle, it doesn't automatically mean you must use hypotenuse leg. Hypotenuse leg is just your most likely to be used one with right triangles. But you can still use angle, side, angle, side, and angle, side. Now, you're going to notice that on this here for congruence of right triangles, we don't have anything about side, side, side on this list. Well, while side, side, side is still perfectly valid, why make a distinction about the triangle being a right triangle and then just completely ignore that and say, oh, all three sides are the same? What we're trying to do here is if we don't see that all three sides are congruent on both triangles, we're trying to prime that pump. So we automatically think, is it possibly a hypotenuse leg? If it fails those three questions at any stage, then we need to look at side, angle, side, or angle, side, angle. And if it's none of those, then we can say cannot be determined. But if it is one of them, then we can say yes by whichever one. And if we're writing our full proof, once I show yes by side angle side, what I must do if I'm writing the proof, my very next step is say that triangle, let's do this one, STU is congruent to XYZ by cool people can teach calculus, right? Corresponding parts of congruent triangles are congruent. Make sure as soon as you make this statement that yes, they're congruent by side angle side, our next step in our proof will always be both triangles are congruent by the corresponding parts of congruent triangles are congruent. Once I can prove one of these criterion, then the entirety of both of the triangles being congruent has been proven. And I have to make sure that my reader knows that the next step in my proof will always be corresponding parts of congruent triangles are congruent. And that right there tells my reader all 6 parts of these triangles are congruent. And when I say 6 parts of any triangle, we have 3 vertices, right? So the vertices are in red. And I just realized I'm not using my annotation tool because it's just completely disappeared off my screen. This is interesting. Oh, I seem to have no way to change colors. Let's see, I've been using pointer options, ink color. Let's go blue, no green. And then so I have, of my 6, 3 of them are vertices, 3 of them are side links. Once I can prove any of these by those 6 points of interest, then I can prove the entire triangle is congruent to the other triangle. So what I want you guys to do is pause the video, and I want you guys to do question number 7. I'm going to do question number 6 because there's something here that I want to talk about. Something I've said 100 times to you guys. Always think of this one property when we start looking at 2 triangles touching. And that is the very first thing I need to do is realize that I have 3 triangles here in this problem. I have triangle TUV. And then I have this line segment US creating 2 triangles. So I also have triangle TUS and SUV. Well, let's do it in the same order, VUS. So now that I can see the 3 different triangles I have here, I can start thinking about a couple things here. I can separate those triangles into these 2, and then I'll see very easily they both have this line segment US in them. Where do we have pointer options, ink color? Right? We can see line segment US is going to be in that triangle and in that triangle. Basically, when I separate these, US will always be equal to itself without a doubt, right? So that would be my pair of corresponding legs. That's going to answer question 3. We kind of skipped ahead here. But yes, I do have 2 pair of corresponding congruent legs. Question 1 is a definite yes because this is a right triangle. And what we would need to know then is that these hypotenuse are congruent. And once I have all of that information, we have a triple yes. So then we would be able to prove that by the hypotenuse leg theorem. For number 7, I want you to comment on this video with your answer. And there's 2 right answers here. So only put 1 up, and let's see if everyone copies the first person who posts, or if we have a nice even distribution of 2 answers. And don't just give me the number, give me the reason why. Right? So like here on this one, I did say yes, 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 and I would say that for my first one, we have a right angle. For my second one, that is, do we have congruent hypotenuse? This is what we need. And that's what the question was asking. And then for the third one, if I was commenting on YouTube, I would say, yes, we have a pair of congruent corresponding legs, and that's because US is congruent to US by the reflexive property. And basically what the reflexive property is a line segment will always be congruent to itself because they're always going to be the same line segment. That's just like saying if you look into the mirror, what reflects back to you will be the congruent version of yourself. And that's part of where the reflexive property comes in. This also tells me that if this is my line of reflection, V will map to T. U and S are on the line of reflection, and we know the identity of a reflection here is that they stay in the same spot. And then we would see automatically that the reflexive property is US is always equal to US. When I fold it over, it stays itself and it maps onto itself at the same time. US is the line of reflection, so through that identity we talked about, we have everything we need for that problem. But fully explain your reasoning here on why you answered number 7 the way you did. If you're saying that there's not enough information or nothing can be determined, tell me why you can't determine anything with this picture. All right. Which statement proves the triangles are congruent using the hypotenuse leg theorem? So it looks like what we're going to be doing. Ooh, let's not use yellow. Pointer options, ink color. Let's go purple. So we're basically going to see, of our 3 questions, what was in our given. And then we're going to look at what part of those givens can be used. So number 1, is it a right triangle? Yes. Let's see, angle F. Oop, didn't know I could do that. And angle B are equal to 90 degrees. So I can definitely say that question 1, are these both right triangles, is a definite yes. For this triangle, I don't know what the hypotenuse is, and I don't know what the hypotenuse is here either. So it's probably going to be this question that we have to satisfy here. Are the hypotenuses congruent? And let's hope that question 3 is we have a pair of corresponding congruent legs. So if I wanted to map ABC onto DEF, I would do a line of reflection through here roughly and then translate it over. And I can see that this would then come to the bottom, right? And then when we slid it over, these would map onto each other. So they are the corresponding congruent parts. So I can say that AC is congruent to EF, and they are corresponding. Now, a lot of you watching this are going to say, Mr. Fimble, we don't need all of this stuff written out for us. I am preparing you for your quarter 2 writing assignment where you're going to be writing a lot of proofs. I want you to see all the information laid out so that you can organize it into your paragraph proof or your 2-column proof. I don't want to just say yes, 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 and move on. So bear with me for that. And let's see if I can do an eraser just to get rid of some of this stuff. So we know that we have a pair of corresponding congruent legs. So this is a yes. So really what it looks like is we're going to be looking for something that shows our hypotenuse is congruent. Before I look at my answer options, I'm going to look at what my hypotenuse is. For this one, it's line segment AC, and for this one, it's line segment DE. So I should be looking for an option that says AC is congruent to DE. Got lucky on the first at bat. I always try and get these, like I say in class all the time, before I look at my answer options, because nothing makes me feel more confident in my answers than if I can do this without a multiple choice option and see that my answer was there. Of course, if my answer isn't there, then I can start picking apart this diagram, or both of these diagrams really, one at a time until I've convinced myself that the option that I will be choosing for my test, homework, exam, or even asking me in tutoring how to do it is believable enough that I can confidently pick it. So then for this to be a yes, we need option A. All right. So this is going to be a fun one for us. I'm going to solve for one of the variables. I'm going to ask you to solve for the other. The way I'm going to do this is, for this to be possible to be solved by hypotenuse leg, I need my corresponding parts to be congruent. So x is a leg, right, because it's not on the hypotenuse, and y plus 9 is a leg because it's not on the hypotenuse. This is the hypotenuse, and this is the hypotenuse. So for this to be possible by the hypotenuse leg theorem, I need to be able to solve for this, and the only way to do this is by substitution. So we're going to go all the way back to algebra 1, and what we're going to do is we're going to set our leg equal to our leg, so that is x, because that's the value of that leg, would have to be equal to y plus 9, and here our hypotenuse of x plus 3 must be equal to 4y. And fortunately for this, we can take what x is equal to and say, right, we know x is equal to y plus 9. So our substitution is actually pretty easy. And that here, I'm going to replace my x with y plus 9. So I'm going to have y plus 9 plus 3, right, because here's my x, and here's this part, and here's this part, is equal to 4y. Let's do a little cleanup here. I don't like the way that looks, and I definitely don't like the way that looks. So, again, my x is y plus 9 plus 3 equals 4y. And now I can do simple algebra, right? This is the simple part of the algebra. This is going to give me 12 is equal to 3y, and that means y is equal to 4. What I want you guys to do is figure out how in the world do we solve for x. I'm going to tell you right now, though, the secret to it is rearranging this to be y equals something, and then drop it into here and solve for x that way. So you're going to do the same thing, but slightly different. Now you need to isolate the y in the top. Once you know what y is equal to, you can go into the bottom and plug it in. I'm going to ask, for your sake, for your sanity right now, don't solve for this one in terms of y. It's just so many extra steps. But put in the chat, in the comments, a separate comment, what you got for x. If there's no value for x, if you get something like 0 equals 1, then that means it's impossible, right? There's no solution. If all your variables drop out and you get something like 1 equals 1 or 2 equals 2 or any true statement, you can just say all reals or infinite solutions. I'm not saying this is going to happen, but I want to make you aware of everything that could potentially happen since we are talking about Algebra 1, and it would not be fair to not bring up those possibilities in there. This is probably the worst double struck R ever written, so let's do that. All right. Like I said, leave your separate comment in the channel, in the YouTube video below. Before we part ways today, I'm going to do two really quick things. I want to talk about an included angle and an included side. So let's say I have a triangle. The included angle, right, is just the angle between two of the sides. So here's side 1, here's side 2, and this must then be my included angle. Now, why do we want to talk about this again? We've talked about it at the very beginning of the school year, and now 9 weeks later, we're bringing it up. And that's just because as soon as I see I have an included angle that has on two triangles, and I can get the corresponding parts here to match up and show that they're congruent, then as soon as I see the included angle, I know automatically I have side angle side. What I'm trying to get you guys to do is start instantly recognizing these as soon as you see something like this. Let's look at that one more really quick. Here I have a triangle, and let's say I know this angle and these two sides. And then over here, I have a triangle. I know this is congruent to that side there, and this is here. I can easily see either one of these can be flipped across. Let's do this one across the line of reflection here. And then that would bring this over to here, this over to here, this over to here. Now I can see my 2 tick marks correspond, my single angle mark corresponds, my 1 side tick mark corresponds. And I can see that in this order I have a side, an angle, and a side. And I know that because I have an included angle. So again, really quick, really easy. I get my original 2 image, my pre-image and my image here. And instantly in my mind, I just ask myself, could I flip this over so those correspond? Yes. I have an included angle. I'm done with side angle side, and I can move on, immediately. Let's look at what an included side is. An included angle is in between 2 sides. An included side is just what's in between 2 angles. So that'd be like this, this, and this. And some of you will already say exactly what this is going to be. Again, I go from an angle to a side to an angle. And we're good to go. I can do this. And I can do this. And I can just see in my mind, if I flip it over, then they're corresponding and congruent again. Let's do one more really quick, just so you can see that they do bounce around, and that's not a problem. I can put it here, here, and here. And then I could have this one, even if it's upside down, right? Here, here, and here. All I have to do on this one is flip it over some imaginary line. And when I say flip it, we know that I actually mean reflect it. This is going to put my single angle marker at the top. It's going to keep this on the left, and this is going to bring it down. And I'm going to be in that same position where it's going to be very obvious after I reflect that I'm going to translate something. And actually, it's pretty obvious that's going to be negative x something, right? We're just going to bring it straight over to the left once it's flipped, and they map onto each other. I have an included side, and that's a visual representation in our congruence criterion of what an included side means. It's stuck between 2 angles. So your homework is on savasrealize.com. It is due tomorrow at 11:59 p.m. There are 2 assignments. No late work accepted in quarter 2. So make sure you have it done. Of course, if you don't, there will be ways to make up that grade as we continue through the quarter.